Dr. Lindsay Bleem, a research scientist from Argonne National Laboratory, and she's going to tell us about constraining cosmology using galaxy clusters in SPT Sunyaev Zel'dovich survey. Thank you for accepting this invitation. Please go ahead.
Thank you very much. I'm very excited to be able to give a talk. I've never given a webinar before, so new experience, so please speak up if I go too fast or I talk too quiet or anything like that. With that, let's begin. So I wanted to give just a brief outline before I jump straight into the talk. So I'm going to give a brief introduction today of what cluster cosmology is, why it's exciting, why I work on it, and then specifically focus on what I do with the South Pole Telescope cluster sample. Finally, I'm going to conclude with what's next, what we're looking forward to, multi-wavelength combinations cluster studies with the South Pole Telescope, DES, and next generation surveys. So just to remind you of something I'm sure you all know, but we live in a really exciting time in cosmology where we have all these fantastic probes from the cosmic microwave background, from the distributions of galaxies measuring large-scale structure, from standard candles like type 1a supernova, which are telling us that we live in this flat universe whose density is dominated by dark energy. But the thing we don't know, what 72% of our universe is. What is this dark energy? Is it simply the cosmological constant? Or what we're seeing is really a problem for theorists when there's about 120 orders of magnitude difference between the predicted density and what we observe today? Is it quintessence? Are we seeing potential energy of a dynamic scalar field? We've seen experimental evidence for the scalar fields before, such as the Higgs, and they could be potentially variable in time or space, so this is something we can look for. Or finally, is it a modification of GR? When Einstein wrote down his equations, we know he didn't get them quite right. Is that what we're seeing? And one way we can do this is we can use clusters of galaxies to study this. We can use the growth of structure. And I really like this figure from this older review paper because it demonstrates this effect. So what we're showing in this top panel here is what the universe would look like as we look back in time, starting at redshift 1.4 in this figure, if we lived in a matter-dominated universe with no dark energy. And so at redshift 0 in the local universe, we see an abundance of clusters. But as we look back in time in this matter-dominated universe, there are less and less clusters. Now in contrast, if we instead look at a universe that looks more like what we think our universe looks like today, one that is dominated by dark energy and less by matter, what we see is a very different picture. So we see the same distribution of clusters at redshift 0 today. But as we look back in time to higher and higher redshifts, we see more clusters. This accelerating expansion of the universe retards the growth of clusters. So in order to form the same density we see today, clusters had to start forming earlier. So to make this a little more quantitative, when we want to study dark energy with cluster abundances, this is what we're doing. The number of clusters as a function of redshift depends on the matter power spectrum, which we typically report in terms of sigma 8 for clusters, the growth rate of structure, and then finally the rate of expansion of the universe. And on the right panel here, in this figure by Joe Moore, I'm showing exactly this effect I showed in the cartoon figure in the previous slide. And this is now for a model survey like the South Pole Telescope, which, as I'll describe, can find clusters out to the earliest epochs at which they formed. And so when we look back in time to higher and higher redshifts, we can disentangle the differences between the cosmological constant, where the dark energy equation of state would simply be -1, and other models for dark energy, because the cluster counts are different. So in a nutshell, cluster cosmology is actually quite simple conceptually. All we need to do for cosmology with clusters is to find the clusters out to high redshifts as best, and then the trickier part, as I'll describe later in this talk, is we need to understand their masses in order to connect them properly to our cosmological models. So historically, there's really been three main approaches to this problem. There's a lot of other clever tricks, but the three key approaches are as follows. People look for clusters in the optical, seeing these extreme overdensities of galaxies, particularly red sequence galaxies. They've seen them in X-ray surveys, looking for extended sources of X-ray emission. Clusters are very X-ray bright. And finally, the newest player in the game is looking through clusters through the Sunyaev Zel'dovich effect. And I show these two panels from a recent review by Weinberg et al. Because I think it's really exciting and demonstrates where the field is going. So in the left panel, what I'm showing, and unfortunately I don't have a pointer here, is the x-axis is redshift, of course, and the y-axis is the limiting mass at which these surveys are sensitive.
Linda, you can use your cursor.
I can in this keynote.
Oh, okay, all right.
So what you can see is that optical surveys are really excellent at finding clusters out to the redshift at which they have flux sensitivity. So Sloan, about redshift 0.3, 0.4, RCS2 and DES, pushing out to redshift 1. The X-ray surveys are flux limited, so their limiting mass rises as a function of redshift. But finally, the new SC surveys provide essentially a mass-limited cluster sample. So for SPT, that mass limit is around 3 times 10 to the 14. And with the new generation of SC surveys shown in the right panel, SPT pole and ACT pole, this is extended to lower mass, which will correspondingly give us more and more clusters in higher redshift. Today I'll be focusing mainly on results from SPT and the dark energy survey. So why am I, as a CMB experimentalist, talking about clusters? Well, the result is actually really cool because the entire history of the universe is imprinted on the cosmic microwave background. From the earliest times, with these new polarization experiments, SPT pole, CMB pole, BICEP, we're looking for signals of inflation from the very, very beginning of the universe. We're looking for these in the cosmic microwave background that picture recombination around redshift 1100, a few 100,000 years after the Big Bang. Now, as these CMB photons travel to us from the surface of last scattering, they can interact with matter along the line of sight. So they are gravitationally lensed by all the galaxies along the line of sight, which gives us a really nice probe of structure with the lensing kernel peaking around redshift 2. And finally, they can interact with the hot gas in clusters of galaxies, which gives us a really nice picture of the last 10 billion years of the universe. And here at Argonne, and I know in Brazil as well, we're involved in a number of these large survey projects. From the CMB side, I'm a member of the South Pole Telescope Collaboration. And here we're involved with DESI, with DES, and with the next generation optical survey, LSST. So the Sunyaev Zel'dovich effect, how we find clusters in the cosmic microwave background, is actually quite simple. So you have the cold microwave background photons come in, and they simply inverse Compton scatter off this hot 100 million degree gas that's trapped in these deep potential wells of galaxy clusters. When the photons scatter off this gas, these electrons, they get a kick in energy, which distorts the CMB spectrum, which is shown in the right-hand panel with the distortion to the right. So now if you difference that initial spectrum, the perfect 2.73 Kelvin black body, from this distorted spectrum, what you see is in the bottom panel. So at low frequencies, where the photons predominantly were, you see a decrement in the intensity of the CMB at the locations of clusters in the sky. Whereas at higher frequencies, where the photons were shifted, you see an increment. Now, SPT-SZ, the experiment I'm going to talk about primarily today, was designed to find clusters. This was one of the primary goals of our experiment. And so we chose bands, which are accessible through ground-based windows, designed to look at this SC decrement and then straddle the SC null. One reason that the SC observable is powerful for clusters is that the scattering process, the intensity you see, is independent of distance. So we can see clusters out to the highest epochs at which they form for a given mass. We're only limited by the noise in our maps. And the other reason, which is key for cluster cosmology, is that this SC observable is tightly correlated with the mass of the clusters. So I've just, on this slide here, showing you the equation for what we observe. And this integrated signal is proportional to the total thermal energy of the cluster, which is tightly coupled to its mass. And simulations and observations have borne this out, showing that the scatter between the SC signal and the cluster mass is about 10%. So it's a really beautiful proxy for measuring cluster mass. So the results I'm showing you today, of course, are not just of my own work, but the efforts of many people, about 50 people in the SPT cluster collaboration, many of whom are shown in this slide here. And we conduct our experiment at the South Pole, with the South Pole telescope. We're about 1 kilometer away from the South Pole. And at the South Pole, we constructed a 10-meter submillimeter quality telescope, which we used to observe at 3 frequencies. 90, 150, 220, which I also call 100, 150, 220. And this 10-meter mirror is critical because this sets the resolution of the telescope, of our camera on the sky. So we have about a 1 arc-minute beam, which is perfectly matched for identifying clusters at high redshift. We're going through 3 generations of cameras on the South Pole telescope. The results I'll be presenting today come from that initial SC survey, the 2500 square degree SPT-SZ survey, which commenced in 2007 and ran through 2011. In 2012, we were excited to upgrade that camera with a new polarization sensitive camera, SPT Pole, and we're very excited that this austral summer, starting in December, we'll actually be deploying a brand new camera, SPT-3G or 3rd generation, which will have an order of magnitude more detectors and sensitivity on the sky. So really exciting things are coming down the pipe. And I'd just like to point out, since you guys can't see me for scale on this webinar, I'm wearing a red coat there, so it's actually a quite impressive size telescope. All right, so why do we go to the South Pole? Well, it's really quite a simple reason. This aerial view shows we go to the South Pole for the weather. So the primary contaminant for millimeter wave experiments like SPT, which observed from the ground, is water vapor. So in the right-hand panel here, I'm showing you what the typical water vapor is, transmission in the atmosphere is from the South Pole. And you might see a wing coming up from the right. That's the wing of a water line, which would completely swamp the signal, for example, if we were at Chicago. So there's really the best place on Earth to do millimeter wave astronomy is from space, like the Planck satellite, but it's very, very expensive, almost prohibitively expensive, to launch a 10-meter telescope up into space. So if you really want to do high-resolution millimeter wave astronomy and grind down for years to achieve the sensitivity we need for our science goals, you need to go somewhere like the South Pole or the Atacama Desert in Chile, where there's a number of other millimeter wave experiments like ACT and Polar Bear. Okay, so we built the telescope, we put in this awesome camera, and then we spent 5 years integrating down, over and over, scanning the sky back and forth, step, back, forth, step, to survey 2,500 square degrees, roughly a 16th of the sky, to produce the SPT-SZ survey, with final depths in our primary science channel, 150 gigahertz of 18 microkelvin arc minute. And this is what that data looks like. So I love this flip-through slide just to compare the evolution of the CMB experiments. So in this first slide, I'm showing you results from NASA's WMAP satellite, which produced fantastic cosmological results we've been using for the past decade. So this is a 50 square degree patch and the SPT footprint. And now we look at the same patch of sky in Planck. So it really sharpens up. Planck has about 2 times the angular resolution of WMAP and 7 times deeper, of course, over the full sky. But what you can't do from space, what you can do from the ground, is this grinding away high-resolution data to produce this image. And I hope this comes through over the web transmission. But just to show you, all these fantastic point sources pop out. I hope you see some shadows, just even in this unfiltered map, showing where the clusters are. This is what high-resolution data from the South Pole brings. Now we lightly high-pass filter this because if we're interested in small scales, we don't need to be looking at the primary CMB, and those features really pop out. So of course we do have some residual CMB anisotropies, both primary and secondary anisotropy. We have these really bright emissive sources. So these are most frequently active galactic nuclei. But once in a while, we're finding some of the most distant star-forming galaxies in the universe. And we have these really cool programs to follow these up further with ALMA, both to study star formation and the evolution of galaxies at redshifts 5 to 7, as well as to understand dark matter substructure using these gravitationally lensed systems. Finally, the reason I'm talking to you today, what I most love in the survey, are these clusters of galaxies. This is the SC effect in action, these shadows in the microwave sky that are imprinted by these clusters. So I'm a CME experimentalist. One of the most important tools in our toolbox is power spectra. So when we have maps like this, one of the things we do is we take a Fourier transform. And this is what we're showing here. This is the results from the Fourier transform of the full 2500 square degree map from SPT-SZ. And at large scales, to the left of this figure, you're seeing the primary anisotropies of the CMB, which are really sensitive to cosmological parameters. These really help pin down our cosmological models. Now at the right-hand side, you can see where Planck really falls off and where SPT's strongest power really is at small scales, where we are both sensitive to further out in the damping tail of the cosmic microwave background. And I encourage you to look for our polarization results, which are coming soon, because they beautifully demonstrate this effect further. But also everything else, all those point sources, those radio sources, those clusters, astrophysics, and cosmology. And in this figure here, I'm showing you the contributions of every single point source and every single cluster, except for the brightest ones, to the SPT maps. I told you I was going to talk about the galaxy clusters in the SPT-SZ survey. Well encoded in this figure, they all are. So what this figure is showing is the power spectrum, the cross spectrum of all the SPT bands. So the 95 gigahertz, the 150 gigahertz, the 220 gigahertz, all crossed with each other. And when you have this range of frequencies, you can piece out the contributions from all the components in the map. So of course we know the CMB spectrum, and that's coming in from the left and falling hard. But there's also these radio sources, brightest at 95 gigahertz, much fainter at 220. The dusty star-forming galaxies, brightest at 220 gigahertz. And then these clusters, which have no signal at 220 gigahertz and are bright at 90 and 150. And there's tremendous statistical power in this data. If we knew exactly how this SC signal related to massive clusters, we would have constrained sigma 8 to a fractional precision of 0.5% with this power spectrum data alone. Unfortunately, we don't have that great of models for how cluster gas actually behaves in clusters. So instead what we can do is we can take this really constraining data and we can place limits on feedback in clusters, on AGN and supernova feedback in clusters, feedback into the hydrodynamical simulations that help inform our cosmology. So that was all the clusters. Let me talk about the most massive clusters, which I hope you could pick out a few by eye in the earlier slide. Of course, we don't find clusters by eye, as fun as that is, when we're systematically searching the SPT survey. What instead we do is we construct a match filter. We know what the noise sources in our map are. In this case, we treat the CMB as noise, all those point sources as noise, and instrumental noise. We know the shape of the cluster, so we can design a multi-frequency match filter in Fourier space to optimize our detection of clusters and pull them out. This was done first in 2008. This was the first blind detection ever of the SC effect, which was done by the South Pole Telescope. And this figure really demonstrates why you needed an instrument with the sensitivity of SPT, like SPT, and the resolution. So in the top panel, I'm just showing you what the raw CMB data looks like at the locations of these clusters in the map, with the beam in the upper left plot for scale. And then you hit these with these match filters, and I really like the third column over 0509 because it really demonstrates the effect of this match filter where cluster is completely invisible, dominated by primary CMB. You filter it, and then you see this decrement at 150 and 90 gigahertz, and then the SC null. And these are incredibly small fluctuations in this map. These are only a few hundred microkelvin riding on top of that 2.73 Kelvin backbody. So it really takes the combination of angular resolution and depth to find clusters. So we've gone a long way since 2008, and today there are over 500 clusters in the SPT-SZ sample, and another 500 in the SPT pole sample, which I'm not going to talk about today. And one of the beauty and the challenges now of the SC effect is, for cosmology, we need to know where these clusters are. So we found their 2D location on the sky, but we need that third component. We need the redshift, which you obviously can't get just looking at this figure. I could not tell you what is a nearby cluster and what is a distant cluster. So in order to do this, we undertook an intensive multi-frequency imaging campaign to understand the clusters from 2008 to 2011, where we used telescopes ranging from the 1-meter slope telescope at Las Campanas up to the 8-meter class Magellan telescopes, and then a large Spitzer follow-up program to get those highest redshift clusters in the infrared. And so this is a project I led, which we published last year, and this is the results from that cluster search. This is the 2,500 square degree SPT-SZ cluster sample. And I love this figure because it really demonstrates the power of a high-resolution SC survey. So what I'm plotting here is redshift and mass for fixed cosmology, which allows me to put a look-back time on that top plot. And so what you can see is that X-ray surveys such as ROSET or CMB surveys such as Planck, which have a limited resolution, so 5 arc-minute beam, which really washes out small-scale features, have this rising mass limit with redshift. Whereas an SC survey, a high-resolution SC survey, allows you to find clusters independent of distance. So from this first cluster surveys, SC selected clusters discovered in 2008, now there are over 1,400 SC identified clusters from Planck, the South Pole Telescope, and the Atacama Cosmology Telescope. So I did a bit of a cheat here when I plotted the mass. This is one of the trickiest parts of cluster cosmology. So let me tell you how we're handling this on the SPT survey. So this is the fundamental problem with clusters, is how do you find the mass of this object? Or this object, or that object, or that object? How do we relate the observables we see in the X-ray, the optical, or the millimeter waves to the mass, given that the majority of the cluster's mass, something like 85 to 90%, is actually invisible in the form of dark matter. So somehow we have to relate this gas signatures we're seeing in the SC to the total mass of the system. And for SPT, we've chosen to tackle this in 3 different campaigns. The one we've been using so far and really leaning on heavily now is based on our large X-ray program with Chandra. So we were awarded an XVP program, an X-ray visionary program, which Brad Benson was the PI on, for 2 megaseconds of Chandra time to follow up with Chandra and get something like 2,000 counts for the 80 most massive clusters in the SPT-SZ survey above redshift 0.3. And with this X-ray data, we can place constraints on the gas mass, the temperature, get a YX observable, which we can then tie into 30 years of X-ray efforts to calibrate the mass X-ray observable scaling relation. And this is really the cornerstone of what we've done so far for our cosmology results. But we want to move beyond that. We want to study the masses directly for our own clusters. And to do that, we've undertaken a dedicated weak lensing campaign getting something like 50 clusters using the 8-meter class Magellan telescopes with the MegaCam imager. And then finally, about 50 more clusters now. We are actually recently awarded another HST program to do clusters above redshift 1.3 to really directly measure the masses of these clusters using weak lensing. And these results, a number of these results, they've been in progress for a few years now, and a steady train of them should start coming out by the end of the summer. Finally, a much more accessible, less observationally intensive campaign, we've also been working on getting dynamical masses, using the galaxies as tracer particles of the gravitational potential from a 3-year NOAO survey. First results were published in Bouquet et al. For Cosmology, and coming very soon to the archive. The paper's under referee now. We're releasing all of the spectroscopic data for thousands of galaxies from 90 SPT clusters, which we've obtained dispersions and spectroscopic measurements for. So keep your eyes peeled for that. Now let's talk about our cosmological analysis, what we've been doing and how we're constraining cosmology with these mass calibrations for the SPT survey. So in order to constrain cosmology, what we're doing is we're taking an MCMC approach to simultaneously vary cosmology and that cluster mass observable relation simultaneously while accounting for the SES selection, dealing with the noise boosting and all that in a self-consistent way. And in our cosmological chains, there are 9 parameters. We have to normalize the X-ray scaling relation parameters, the SC scaling relation parameters, the normalization, slope, possible redshift evolution, the scatter in these X-ray and SC to mass observables, and any correlated scatter between the X-ray and the SC, of which you would expect there to be some. In addition to that, we're simultaneously constraining cosmology. So we start with a base lambda CDM cosmology and really nail those parameters which clusters are sensitive to, sigma 8 and omega matter, as well as look at various model extensions. What can we do combining the CMB with SPT cluster data? And this is the evolution of our results. So what I'm showing here is how the SPT cosmological results have evolved from the first cosmological paper by Brad in 2013 to the recent paper we put out this spring. And this first slide is just assuming the same mass calibration. And what you see is that as we've added more clusters through the years, from Benson 13 to DeHaan 16, that diagonal area has really shrunk by the addition of these new clusters. We're better constraining the shape of the mass function. Now this other axis here is really limited by our systematics and our mass calibration. And so what we've seen is through the years, this mass calibration has actually evolved and been improved. So our recent weak lensing net calibration increases the mass calibration by about 10% relative to previous results. And this is related to a number of things, complicated in the weak lensing analysis with shear multiplicative bias, as well as new data in the cosmos fields, allowing us to put better constraints on what the photo-Z distribution of the background sources is. But this remains, this weak lensing limitation remains the key limitation for SPT cosmology, which is why we're pushing so hard on that mass calibration with MegaCam and with HST and with the dark energy survey, as I'll mention in a minute in the future. So to put these results in the context of other surveys, this is what we're finding. So in the left panel, we're simply plotting sigma 8 omega matter for SPT and comparing it to the Planck, recent Planck results, Planck plus WMAP polarization. And what we're finding, unlike some other recent cluster results, is that we are completely consistent in our sigma 8 and omega matter constraints with the Planck cosmology. Additionally, we are also consistent with some other cluster cosmology projects such as Weighing the Giants, which are also weak lensing calibrated. Now cluster's real power comes, as you can see in this slide, Planck is giving you a tremendous constraint on sigma 8 when you assume that you are in a lambda CDM cosmology. However, CMB has significant degeneracies if you loosen that knob, if you allow W to float and assume that we aren't in a cosmological constant universe. And so what I'm showing here now is the constraints on the dark energy equation of state W versus sigma 8 for standard candles, standard ruler measurements, which is that gray band, H0, BAO, and supernova form that band. And then you can see the CMB from Planck comes in. And there's a large degeneracy between W and sigma 8. However, when you add these cluster measurements, which are constraining the growth of structure, they help break these degeneracies and allow a more precise measurement on this dark energy equation of state, which we're finding to still be consistent with -1. But there's a lot of room to improve here as we tighten up our mass calibration. Finally, there's also a strong degeneracy in CMB between sigma 8 and the mass of the neutrinos. So again, clusters with their constraints on sigma 8 can also improve our understanding of the neutrino mass scale. So this program is ongoing. We've been working on this since 2008. And in the coming years, with our mass calibration program to be worked out, which we've worked out, when it comes to fruition, with just the SPT-SZ sample, CMB and cluster survey will constrain these constraints on dark energy to 7%, independent and complementary power to constraints from standard candles and standard rulers, and even better when you combine them together. So this is going to be really exciting in the coming years. Okay, so finally, let me talk about one more really, really awesome thing that's going to happen with experiments like SPT in the near future for this mass calibration. So weak lensing is really the gold standard for cluster mass calibration. You're directly measuring the masses. But as I showed you in our previous slides, there's still quite a few shifts that can happen as we work out systematics and the multiplicative bias of the shear measurement and the photo-Z distributions. And this is all being tested right now with the dark energy survey. But the CMB itself is actually going to be a fantastic tool for these measurements in the near future. And that's because these clusters, like all other matter, gravitationally lend to the cosmic microwave background. So what happens when you have a massive cluster and you put it on a gradient in the CMB, I show these two figures here. You probably can't see the difference by eye, but let's look at the difference. What you can see is that the lensing makes the photons, the CMB photons, appear to originate further from the center than the cluster than they actually do. So the cold side of the gradient looks hotter, and the hot side looks colder, which produces this characteristic dimple in the cosmic microwave background at the location of clusters. This is an incredibly subtle effect. I hope you notice the y-axis scale on the right side is in microkelvin. For a 10 to the 15 solar mass cluster, we're only talking signals of a few microkelvin. But when you have these deep surveys over these wide patches, you can actually stack this data. You can combine the signal from all the clusters and pull out this effect. So with SPT, with the Planck survey, and recently with the X survey, we've all just come up with the sort of first 3 sigma-ish detections of the lensing in the cosmic microwave background using clusters. But this tool is only going to grow as these next generation surveys get 10 or 100 times more sensitive than current generation. And with cluster lensing, you lose many of the systematics, gain new ones, but just have different systematics than you do with the optical weak lensing surveys. We know the source redshift. The CMB is at redshift 1100. We don't have to worry about losing background sources as we go to high redshift. So this promises to be one of the most powerful tools which you will have for doing weak lensing of clusters above redshift 1. And finally, this comes for free. When you do a high resolution SC cluster survey, you are getting this fantastic CMB lensing data. So we're able to calibrate our masses using our own survey data. Okay, so let me jump into one of the next most exciting things I think is really the future of clusters cosmology with millimeter wavelength surveys and optical surveys. Particularly, I'm going to focus on several examples from the Dark Energy Survey and the South Pole Telescope. So as I'm sure you all know, the Dark Energy Survey has been running for a few years now on the 4-meter Blanco telescope in Chile. is this ongoing optical survey, which will cover 5,000 square degrees. And in the optical, it will find roughly 100,000 clusters out to redshift 1. And in this really rich optical data set, there'll be a number of probes of dark energy that will just go an ongoing cluster survey, weak lensing results, BAO, supernova. And one of the bonuses from my perspective is that the survey was coordinated to overlap with the South Pole Telescope. So it is hitting our 2,500 square degree patch, which will enable a lot of really interesting multi-wavelength science, and has already enabled if you go look at the archive. And this is critical as we're getting into this era of precision cluster cosmology, as we want to constrain sigma 8 to sub%, as we want to know omega matter, as we want to test models of dark energy, we really need to understand the systematics in our measurements. We really need to understand the systematics in terms of mass calibration for clusters. And these are some older figures, but they really demonstrate the power of what you can do when you combine an optical cluster survey and an SZ cluster survey. And this is results from the Planck and the ACT collaborations. But what I'm showing here in the left-hand panel is going to the Sloan Digital Sky Survey, taking their optical cluster catalog, stacking and extracting the SZ signal at the locations of all the clusters, and comparing it to a model which was based on previous models of what the weak lensing mass implied for those optical clusters and what the mass-SZ signal relation was assumed to be for those clusters. And you can see is there's a tremendous discrepancy between the predicted signal based on all the best understood mass scalar relations at the time in 2011 and the observed signal. Similar results were measured in the ACT survey. And so this really pointed to the fact we didn't understand our systematics as well as we thought we did. And the puzzle was actually really interesting how this was resolved, because it has been resolved. And it involved pieces of weak lensing calibration, photo-Z distributions in Sloan. It involved hydrostatic bias in clusters, not getting that right, not understanding selection functions, just all these intricate pieces that have to be well quantified. And this is just pointing the way at things we can do with next generation surveys to really give us trust in the observations we're making and the cosmological constraints we're extracting. And we're doing that right now with the Dark Energy Survey. We're leveraging all this high-resolution South Pole Telescope data to study the mass-richness relation of Dark Energy Survey clusters. Both in the left-hand panel, I'm showing you results from high-mass South Pole Telescope clusters, which we found in the 2,500 square degree survey, which we matched to Dark Energy Survey clusters. Just demonstrating that there is a lot of signal and that we can constrain the scatter. This has been one of in the observable richness to mass scaling relations. This has been one of the troubles for optical surveys in the past, is how do you relate that few % of the mass in the galaxies to the overall cluster mass. Gas observables have had a much tighter proxy, but there's been a tremendous amount of progress in the optical community, and by testing these against gas observables, we can help constrain and measure how far this progress has come. And this is critical for cosmological constraints from optical clusters. Now going to the other end, what about those low mass clusters? What if we repeat the experiment that Planck did now in the SPT data? So taking red mapper clusters, red sequence selected clusters, and stacking the SPT maps at their locations in the SC data. And what you can see here is even going down to low richness, about 10 to the 14, solar masses is about lambda 20, there's tremendous signal in the SPT maps. But again, understanding how to model this whole process is complicated. I encourage you to go look at this paper. I truncated this figure to fit on the slide. But what we predict and how we extract that data from the SC maps is incredibly sensitive to the assumed mass calibration of the optical scaling relations. So with these sort of consistency checks, we can provide confidence that we are doing the right thing and that we understand the gas physics in these clusters. Working with DES also enables exciting new science. And I love this movie here. This is a movie created, this is from one of the largest n-body gravitational simulations in the world that was created at Argonne, because there's a tremendous amount of information, not just in the location and abundance of clusters, but their relative motion as well. Clusters, of course, are tracing the growth of structure. They're fantastic probes of gravity. And so we can actually measure this velocity, the movement of clusters on the sky relative to us, using a second SE effect, not the thermal SE effect, but the kinematic Sunyaev Zel'dovich effect. So again, this is caused by CMB photons scattering off electrons in clusters, but this is now scattering off all the electrons with peculiar velocities with respect to the CMB rest frame. There is no spectral dependence to this signal. It can be both positive or negative, depending on the relative cluster motion with respect to us along the line of sight. And it is much, much weaker than the TSC effect, about 20 times weaker at the high mass end, where we're able to individually detect these SC clusters. And because the thermal SC falls as mass to the 5/3, the signal actually becomes comparable for low mass groups. And it's been incredibly hard to detect. So what I'm going to show you on this slide is all but one, which I'll highlight later, of the detections of this KSC effect for clusters. So what we're showing here is this recent result from 2013 by Sayers et al., where they had an extremely unusual merging system, where they had a subgroup screening into the cluster at a few thousand kilometers per second. So with high-resolution HST weak lensing data, with Chandra X-ray data, tremendous amount of spectroscopic data to model the system, they were able to model on their CMB data from Bolocam the fact that they could see a small detection, about 3 sigma potentially, of the KSC signal in this cluster, this relative motion. More recently, more robustly, is instead of looking in individual clusters, to look in aggregate samples. Now you can't stack like we can do with the thermal SE effect, because the motion can be positive, the signal can be positive or negative. But instead what you can do is this really clever trick, which was first published by the ACT collaboration in 2012, where you can take the relative motions of pairs of clusters. And that's illustrated in this bottom panel here. So when clusters are moving away from us, the CMB looks slightly colder. When clusters are moving toward us, the CMB looks slightly hotter. Now clusters on average should be falling towards each other because of their mutual gravitational attraction. So you can set up a pairwise estimator to difference the CMB signal you see between pairs of clusters and extract that as a function of separation. And that first result, which is a really nice result, is shown in this top panel here, showing the co-moving separation and the pairwise KSC signal. Incredibly small, 1 microkelvin, but they were able to detect it by using hundreds of spectroscopic measured systems from blocks. So this is really exciting. This is sort of following the trend of, last year's first detections become this year's cosmological constraints becomes next year's foreground. But this is a really exciting area of study to model it at Argonne using simulations. So this is work which I contributed to, led by my colleague Sam Flender at Argonne, where we took that large n-body simulation and we made a mock CMB sky consisting of primary CMB, the thermal SC. Of course, we know all the motions of the objects in the system in the n-body simulation, and we combine this into a map to make a full sky mock CMB. And then we use this to understand what we actually measure when we measure these pairwise KSC signals in the CMB sky. So what we're showing here in the top panel is one of the results from that paper, showing, again, that co-moving separation versus the temperature, where, of course, clusters of galaxies are moving towards each other, so the signal is highest at small scales. And this is just showing now is complicated. So there's a lot of gastrophysics that goes into this. And depending on what models you assume for the gas, whether you assume that it's in hydrostatic equilibrium, where you put in that, the signal traces the density, whether you put in models that include star formation, AGN feedback, you get different results. So if we want to turn this KSE measurement into a precision cosmological measurement, we need to understand the gastrophysics of clusters. On the other hand, we can do exactly what we've done with the power spectrum measurements and say, well, we can constrain cosmology incredibly well from the CMB, from cluster counts, from BAO. Let's use this pairwise KSE effect to really pin down astrophysical models of clusters, to really understand what's going on in clusters. They give us a new probe, and I think this is one of the most exciting potentials for this data. Besides interpreting results, in part of interpreting results, we also have to understand the biases that can arise from these measurements. So one of the really exciting things we've done with the dark energy survey, it's not a spectroscopic survey, but there's really good redshift estimations on the clusters, about 1 to 2%. So one of the things we can use simulations to do is to understand what happens when we measure this signal on real data. So this bottom panel is showing here how your signal changes is a function of how well you can actually measure those optical cluster redshifts. Of course, it's very strong with the true Z, but then you're degrading your ability to tell which cluster is in front or behind of which other cluster as a function of redshift error. And so this is just showing how your measured signal degree is a function of your measurement accuracy. So with these simulations, we folded them in, and I'm very excited that we recently published the first measurement of this pairwise cluster motion using optically selected clusters from the dark energy survey with photometric redshifts. So this is one of the highest signal-to-noise detections of this signal to date, using year 1 DES data, of which there will be, of course, 5 years when the survey reaches full depth. And so this is really pointing to the promise of this data set for being a precision probe of astrophysics in the future. We're just getting started. This is something that's going to take off over the next 5 years. So what's next? I mentioned all these cluster surveys. I've highlighted stuff that's only going to get better. How is it going to get better? Why is it going to get better? Well, that's because everything's evolving. We've started in 2007. I've shown the results. All the results have been from a cluster survey that started 8 years ago. But since then, we've rapidly increased the sensitivity of our CMB experiments. For CMB experiments, detector sensitivity has been essentially limited by photon shot noise for the last 15 years. And we've just been upgrading by building more and more and more detectors. So for this coming year with SPT-3G, we're deploying a trichroic focal plane with 16,000 detectors. It's going to have 10 times the sensitivity of SPT-SZ. So all these measurements that I've shown you are only going to get better. In the same time, of course, the other surveys haven't stood still at all. So we've gone from Sloan to the dark energy survey, more detectors, fantastic camera, bigger telescopes, and soon we're going to have LSST, which is going to be just a transformation in the field of optical survey astronomy. For future cluster surveys, the future is fantastic because of all these improvements. So with SPT-SZ, we have 516 clusters. Throw an SPT poll, we get something like 1,000. 3G, showing in this left-hand panel here redshift versus mass, just a projection of what the cluster samples will look like. For 3G, we expect over 10,000 clusters, with 1,000 of those clusters coming from redshift 1, above redshift 1. So really opening the window into the high redshift universe. We'll lean heavily on optical surveys, such as the dark energy survey. SPT-3G will survey the same patch, and LSST to help us identify the optical counterparts and obtain redshifts for those clusters below redshift 1. Above redshift 1, we need near-infrared, and we're still working out the details of how we're going to handle this large near-infrared follow-up program. Like I mentioned earlier, this deep CMB data will also enable CMB cluster lensing. It's a competitive mass calibration tool for dark energy science. So for SPT-3G, we're getting something like 3% stacked constraints if we stacked all of those 10,000 clusters and extracted the CMB lensing signal, or about 10% if we just stack those clusters above redshift 1 and completely rely on DES below redshift 1. CMB-S4 is a really exciting program that's just now taking shape. The community is still coming together to figure out how to build this worldwide CMB program, which will feature telescopes at the South Pole and the Atacama, in Greenland, perhaps Tibet, which will have over 100,000 clusters in this full sky survey. Fantastic constraints on the CMB lensing mass relation for those, and of course the primary focus of that will be to really nail inflationary physics and neutrino physics. And so my time is up, so let me just conclude here and say that we found hundreds of these massive clusters with the South Pole telescope. This clean mass limited selection has really led to a fantastic sample for ongoing cosmological and astrophysical studies. What we've found so far is that our cosmological analysis is completely consistent with other cluster studies, as well as Planck's CMB cluster cosmology. To really sharpen this up, we do need better mass calibration, and this work is ongoing. And really, finally, one of the most exciting pathways in the future are these joint optical CMB analyses. These multi-wavelength analyses promise to improve cosmological constraints, test systematics, and on their own enable new cosmological probes. Thank you.
Thank you very much, Lindsay. Very nice talk. So we have time for questions. Questions? I'd like to know how you calculate the completeness, or how do you ensure the completeness of the
Sure. No problem. So let me just pull this figure up. So to calculate completeness, what we can do is we have mock CMB realizations with things like point sources. We can directly measure our instrumental noise using jackknife techniques. So it's really nice. CMB, this is one really nice thing you can't do in the optical, is because we scan back and forth across the sky, if we difference, for example, left-going scans from right-going scans, we remove all of the sky signal from the data, but we're left with all of our instrumental noise. So we can actually get a really nice model of what our telescope and instrumental noise looks like, which we can add to our simulations to make a really realistic CMB sky that we can then populate with clusters and then see how well we can recover what we input. So we do this millions of times to build up our selection function.
Okay, thank you. And did you obtain spectroscopic redshifts for all the 500 clusters?
So we're working on it. I guess I don't have that slide in this talk. But so we have spectroscopic data for 140 of these 516 clusters, primarily focused here. Actually, let me do it this way so I can actually draw on the slide. So we have spectroscopic data for mainly these clusters up here, 140, plus whatever we happen to pick off, which were X-ray or other selected clusters. For example, the Bowler cluster is in the SPT-SZ footprint, so we have a SPECSI for that, of course. This week, I'm actually working on, we've been doing a dedicated follow-up campaign with the upgraded LDSS imager on Magellan, which actually has a DECAM chip. Its red sensitivity is excellent. And so this week I've actually been working on reducing the spectroscopic data from these clusters. So hopefully this will no longer be a lower limit, but very soon we'll actually publish redshifts for this very high redshift sample.
Okay, and so for the ones you only have photometric redshifts, how did you take into account in our cosmological analysis?
So the photoz's, we can quantify their errors using that 140 spectroscopic subsample. And so we treated them as having Gaussian errors with, depends on the camera. So for SWOPE, it's a 1 meter telescope. We went fairly shallow, and it had about 2 to 3% uncertainty on the photo-Z's. Magellan has about 1.8%. We had something like 50 spec-Z's per camera with overlap to calibrate. So that's all folded into the Monte Carlo analysis where you can draw from that redshift distribution and fold it in.
Okay, thank you. More questions?
I have a question. For the cosmological constraints that you showed, you showed plots of omega matter against sigma A, basically. Is this assuming lambda CDM?
This is assuming lambda CDM, that's right.
Do you have any plans to go beyond lambda CDM?
Right, so we did, and we have, so I would definitely encourage you to look at Timon's paper, the Han et al. 16, which is on the archive now. So we did do a number of model extensions. I just showed a couple here. We looked at dark energy, equation of state. We looked at neutrino masses. We looked at ineffective. But yes, that we did do some extensions. And
there's a sign missing here. No,
Sorry.
omega is not this one.
Sorry, I can't hear you.
There is a sign missing.
Oh, yeah. In that figure, there's a -1 here, and there's not one there. Yep, hang on. We're done.
Okay, I take a look at the paper. Thanks.
More questions? I have one more question. You said your results are completely compatible with Planck, but Planck has its own problems, like sigma 8 problems from the temperature, from the abundances.
Yeah, so actually we are completely consistent with Planck, and I'm actually on the right slide right now. But you can see that we're actually fairly broad. So we're also completely consistent with WMAP. In fact, we prefer a WMAP cosmology, but there's no strong tension with Planck. And the interesting thing is the recent tau results from Planck, if you propagate that through to sigma 8, because this is Planck plus WMAP polarization, but if you propagate their new tau constraints, they actually move down here, more towards the central value from clusters, from weighing the giants and from SPT. But I agree that tension in Planck between the lensing measurements and the TT power spectrum are potentially very interesting.
Okay, thank you. More questions?
I have a question. Is there there'll be a new release for SPT soon, anytime soon, with new clusters?
New cluster release. So we have a number of, yes, there will be. So I didn't talk about our new survey, which I am working on right now. I don't have the figure in this talk, but I'll go up here. So we've actually surveyed, I've only talked about results from the 2500 square degree SPT-SZ survey. Actually, the TES slide's the best. But we've actually, during the austral summer, the last few years with SPT pole, the sun is up and it's actually contaminating our main science field for SPT pole. So what we've done during the summer months is we've done what we call our summer field survey. And we've actually surveyed an additional 2,500 square degrees of sky north of the SPT footprint. So we've covered basically here, if you can see where my mouse is tracing. We go up to deck -20, from 23 hours to 5 hours. And then actually, because I got tired of following up at Magellan and not in the summer, not having targets, I talked us into doing 2 fields on the other half of the sky. So we have a 13-hour and a 15-hour field now on the other half of the sky to round out 2,500 square degrees. I am working on that cluster catalog, and I'm hoping it's out this fall, but lots of stuff going on.
Oh, thanks.
But that's also, the really nice thing is that also overlaps with DES and with pan-stars. So there will be a lot of cool multi-wavelength science to do in these regions too.
Yeah.
More questions? Okay, so let us thank you again, Lindsay. Very nice talk. Okay, so thanks everybody for attending this talk and see you all soon. Thank you all. Bye-bye.